Hello viewers, welcome to my channel Chemphilic. So today's video is video number 87 and video number 87 is the 28th episode of Chemical Thermodynamics. Topic of today's episode is heat engine, efficiency and Carnot engine. So let's start. What is heat engine? Heat engine is that machine which can transform heat energy to mechanical work. That means it produces mechanical work from heat. So the machine used for the conversion of heat into work is called the heat engine. Now, heat engine, that means, say, this is a heat source. So this is your source, heat source. And this is the heat engine. Heat engine means it will transform heat energy to mechanical work. So if the heat engine absorbs heat from the heat reservoir or high temperature heat source, and then if it is converting it to mechanical work, W, then that is heat engine. But in my last video, you have seen that this type of heat engine is not possible. Why is not possible? Because the heat absorbed by the engine or this machine cannot be completely converted to mechanical work. A part of it is converted to mechanical work and the remaining part brings some changes elsewhere, either in the system or surroundings. Okay. So, in this process of heat engine is not possible. In my earlier video also I have explained, because in this process a part will be converted to work, another part will bring some changes. Now, you have seen in Kelvin Planck's statement for second law of thermodynamics, there you have observed that if the heat engine is like this, say this is the source, high temperature source, and this is the engine. This is the engine. Okay, here it was the engine. Now, this engine, it is absorbing heat from the source and a part of it is converted to mechanical work, and the remaining part it is releasing to the low temperature sink. This is called sink. This is the low temperature sink. So heat is absorbed from this high temperature, say T2 of the source, which is nothing but a heat reservoir. So this heat engine is absorbing heat from the source. A part is converted to mechanical work and remaining part, the residual part, it is releasing to the sink, which is at a low temperature, say T1. And this type of heat engine is possible. In a cyclic process, it can continuously produce the work because it is taking heat from some source, converting the heat to some extent to mechanical work. Remaining heat it is releasing to the sink. Again, the cyclic processes continue. Okay. So, heat engine running on a periodic cycle can yield work continuously. So, what we have observed for the heat engine? So, in the operation of heat engine, what is happening? Number one, heat is absorbed from high temperature source, which is the heat reservoir. Okay. Second point, what is happening? A part of it is converted to mechanical work, and what about the remaining part? The remaining part is released to the low temperature sink. Okay. So these things we have observed. Now let us take the example. Say for power plant. In the power plant, what happened? This is the heat source, which is the furnace. Okay. From the furnace, this boiler where water is boiled and steam is generated, and here the steam is acting as the working substance in the heat engine. So this heat from the furnace is transferred to the boiler. That means here the steam is absorbing, water is absorbing the heat. Then the steam flows to the turbine. This is the turbine, where it leads to the formation of mechanical work. It is rotating this turbine, okay, with this, because it has absorbed the heat, and it is rotating the turbine, and because of this mechanical work, that means heat is converted to mechanical work, and from this mechanical energy you can produce other energy like electrical energy, etc. So the steam flows to the turbine and leads to the formation of mechanical work. So this is work out, W out, output, out in the sense here output. Okay. Then the residual heat, that steam, this residual heat is transmitted by the condenser. Steam enters to the condenser, and then the residual heat is transmitted by the condenser to the low temperature sink. So here it is atmosphere. Okay. So residual heat is transmitted to the low temperature sink. Then what happens? If the water, when this water cycles back to this boiler by this pump, that means this water via this pump, it cycles back to this boiler, where once again it will absorb heat. Okay, and to transmit this water to this boiler, or pressure is required. That means work is required to transmit this water to this boiler via this pump. That means here W in, you have to produce the work. Work has to be done so that it pressurizes this water to cycle back to this boiler, and once it is in the boiler, once again it will absorb heat from the furnace, and once again the same cyclic process will be continued. So continuously work will be generated, mechanical work or heat will be converted to mechanical work. A part of the heat absorbed by this substance, working substance, here it is steam, is converted to the mechanical work, and residual part is released by the condenser to the, say, atmosphere. That means low temperature sink. Once again this water is cycled back to this boiler via this pump, and whereby it, to pressurize it to go back to the boiler, work has to be done. So here W in. So in this process mechanical work is produced, but as I told you, a part of it is converted to mechanical work. Okay, remaining part it is released to the low temperature sink. So no heat engine is 100% efficient. That means no heat engine can convert 100% of the absorbed heat to the mechanical work. So now we have come to the new term, that is efficiency. So as I told you, no heat engine can convert 100% of the absorbed heat to the mechanical work. That means the heat engine must have some capability or efficiency to what extent it can convert heat to mechanical work. Some machine will convert more, some will convert less, like that. So the fraction of the heat absorbed by a machine that it can transform into work is called efficiency. So fraction of the heat it can absorb, what it has absorbed, that is transformed into mechanical work. So not entire heat. Okay, fraction of the absorbed heat by the machine which it has converted to mechanical work is known as the efficiency of the machine, or here efficiency of the heat engine. Okay. Now we have seen in my earlier just now, here once again if I keep it, see here, we have seen here, this is the output, work done by this substance, working substance. So total output, so W net output if I write, that will be is equal to how much work it has produced minus how much work is done on this, done on the system, on the engine. Okay, so it will be W out minus W in, right? And this one once again equal to Q in, heat absorbed by this working substance or heat absorbed by this engine. What is that? Is Q in. Okay, because why it has performed the work? Because it has absorbed the heat. So we can write it as heat Q in, that is heat transmitted to the engine or to this, here it is boiler, minus Q out, how much heat it has released to the surroundings in the sense low, not surroundings, low temperature sink. Say here it is atmosphere. So here it is Q out. Then your efficiency which is denoted by eta, that will be is equal to, you can write it as this W out minus W in, work produced by the engine and work is done on this working substance of the engine divided by this total heat absorbed, that is Q in, or this one I can write it as Q in minus Q out divided by Q in. Okay, that means it is nothing but this is your W net output. Net output means work produced minus work is done on the system divided by Q in, that is the total heat absorbed. This is the efficiency, right? Now Carnot, a French engineer, devised a technique called Carnot cycle for calculating the efficiency of the heat engine. Okay, this calculation part I will show you in my next video. Now today we will see what are the different parts of this Carnot heat engine. So these are the different parts of this Carnot heat engine. So what is there? The central part of this heat engine is a cylinder. This is one cylinder. Okay, and in this cylinder, this is the cylinder, and these two walls are insulated, right? And this base is not insulated, this is conducting. And this cylinder is attached to a frictionless piston. This is the piston which can move up and down. Okay, and inside the cylinder some working substance is present. In Carnot heat engine, the working substance is ideal gas. Okay. So the central part of the heat engine is this cylinder, which is attached to the frictionless piston, and where this working substance is present. Working substance is ideal gas, and these walls of the cylinders are insulated. Base is conducting. Base is not insulated. Okay. What is the another part? Another part is the source or heat source. This one. This heat source is nothing but the heat reservoir or high temperature heat reservoir, from where this working substance of this cylinder, which is present in the cylinder, absorb heat. Okay, as you have seen. And then a part of it is converted to mechanical work. Here how? It will push the piston. That means expansion will take place. During expansion, work is done by the system. Already you know. Okay. Then, so this source, it has the infinite this capacity. Okay. Infinite heat capacity. That means what I want to tell you that from here, continuously it is absorbing the heat, right? Still, its temperature will not observe. Okay, that means it must have the infinite thermal capacity, right? Now, after making this mechanical work or converting this absorbed heat, a part of the absorbed heat to mechanical work, residual part, it will release to this low temperature sink. And this low temperature sink also a heat reservoir with infinite thermal capacity. Why? Because here heat is released continuously in the cyclic process, but still there will be not much alteration of the temperature. Temperature will not alter. So it has high thermal capacity. Okay, infinite thermal capacity. So this is low temperature sink. What is the another part? Another last part is this insulation stand. That means if this base of this cylinder is attached to this insulation stand, then this entire thing will become insulated. No heat will absorb from the surroundings, or no heat will enter to the system, or no heat will be released to the surroundings. Okay. So, in Carnot cycle, next video I will explain, you will find that there will be 4 steps. Okay, 4 steps and 2 expansion steps and 2 contraction steps. Okay, and in among these 4 steps, 2 are isothermal, 2 are adiabatic. During adiabatic steps, this cylinder is attached to this insulation or insulated stand, so that this system, this part will become insulated. Okay. So, what are the parts we observe in this Carnot engine? First part what we observe is the central part, that is the central cylinder. Cylinder with the working substance, and here working substance is ideal gas. In Carnot heat engine, working substance is ideal gas. Second part, what is the second part? Second part is high temperature heat reservoir, which we call it as source. It must have infinite thermal capacity. Okay. Now, so from the source it will absorb heat. Then low temperature heat reservoir, that we call it as sink. Sink also must have infinite thermal capacity, so that when the heat is released here, temperature will not alter. Number 4, insulated tank. So these are the different parts. Now, what are the limitations or drawbacks in this Carnot heat engine? See here, first of all, here in Carnot heat engine, the working substance is ideal gas. No gas behaves ideally under normal condition. You know that. Under low pressure, very low pressure and high temperature, gases behave ideally. Otherwise, they will not behave ideally. So, considering or taking the working substance as ideal gas, this is not possible. Number 2, second point, this piston is frictionless. You cannot make a piston which is completely frictionless. Okay, that is also not possible. Frictionless piston you cannot make it. Okay, and next point is this, as I told you, that this source and sink, they must have infinite thermal capacity, so that heat is taken from here, from the source, or heat is released, residual heat is released to the sink, but still the temperature will not alter. This is also not possible completely, right? And the last one, in Carnot cycle, all the steps are reversible steps. Reversible steps cannot be carried out practically because the steps are very slow. In that very slow process, it cannot be carried out. But still, Carnot cycle would give an idea about the efficiency of that machine or heat engine. Theoretically, you can calculate that how much should be the maximum efficiency, because you know work done in a reversible process is maximum, and in Carnot cycle all the steps are reversible step. So that part, that idea will get it from this Carnot cycle. Now in the next video I'll explain in details about this Carnot cycle, what are the all 4 steps, and what is the work done or work is done by the system or on the system during each steps. Okay, and the calculation of this efficiency, everything I'll show you. Hope you have enjoyed it. Thank you.